Okay, this is gonna be a two-part video because I'm putting chapters 5.3 and 5.4 together of analyzing polynomial functions. So we went a little bit out of order. We just talked about how to break down any type of polynomial and to solve, but we've never talked about what the graphs look like. So that's what we're gonna do today. So a polynomial function is defined in your textbook by a sub n x to the nth. Now, what that means is a sub n is just a coefficient. It's just a number. All these a sub n's are. And n minus 1 and n minus 2 just means it's descending. We have x to the n, x to the n minus 1, x to the n minus 2. So if I had, let's say, x to the 5th, this would be to the 4th. Don't get caught up in necessarily the definition of what a polynomial function is. But this is what it is defined at. I'm just trying to explain to you as you see these as you get older. Okay, a polynomial functions, they're continuous, which means for every x value, there exists a y value. Technically, if you were to look at the graph, you would never pick up your pencil. There wouldn't be any gaps or spaces. So an example of this would be a quadratic. That's continuous. Okay, a non-example might be like a step function. If you have to pick up your pencil, it's not continuous. Another example would be a cubic, like x cubed. Another non-example would be, can you think of any? If you can, write one here, send it to me, and I'll give you an extra credit point. Okay, polynomial functions are also called power functions because they're raised to a power. A power function is any function in the form with a coefficient of a, x raised to the nth, where a and n are non-zero constant real numbers. It says the domain of a polynomial is, so what numbers can we use in polynomials? Well, we're gonna get an output for y. All real numbers, and we use our symbol r, okay? Which means the graphs go on infinitely. What happens to polynomial functions when the domain values get really, really big and approach positive infinity or get really, really small, what happens, okay, to the output is called the end behavior. Okay, we want to know what happens to the outputs as x gets bigger or smaller. All right, so we're not going to always have a graphing calculator, but we're going to graph with our graphing calculator these four functions. So I want you to go to y equals in your calculator. Some of you are still new to this. Okay, this one's a little dirty. And hit y equals. And I want you to put an x cubed, x, this caret button is raising it to a power of 3. Why is not coming on? Well, this calculator died. Okay, so you're going to put in your function. And when you graph it, I just want you to sketch the general shape. It doesn't have to be perfect. Okay, so was this an even or odd function? Okay, it's an odd because it's raised to the 3rd. Was it positive or negative? Our a value in front was greater than 0, so yes, it was positive. Here, this is an odd function. It's negative. This is an even function, it's positive, and this is an even, and it's negative. So I want you to pause the video and go ahead and fill this chart out and come back and look. Okay. These are not perfect. I don't care. I just want the end behaviors. So we notice that if you were an even function, you're going to have this parabola type shape where both ends are up or down. And when you have an odd function, one arm is up and one arm is down, and it flip-flops whether it's positive or negative. Okay, so let's take what I just said and summarize it in this table here. When a degree is odd, one arm is up and the other down. When the degree is even, both arms are up or down. When the leading coefficient is positive, that right arm goes up. And when the leading coefficient is negative, that right arm is down. That's just kind of layman's terms to say it like that. It's not really professional or sophisticated. So how we're going to say these arms is what the end behavior actually is. Is it going to positive infinity or negative infinity? So let's look through these three. Let's just draw a general sketch of what they would look like. This is even, so we're going to draw it as a parabola, but it's negative, so it's going to go down. This one is x to the 5th, so it's like x cubed. This one's x cubed, the leading term, but it's negative, so it's going to flip-flop. All right, now looking at all of these, where do the ends go? My ends are approaching negative infinity. My ends here are approaching negative infinity and positive infinity, and vice versa here. Now, if I asked you for the end behavior here, you could say negative infinity. But if I asked you for the end behavior here, would you say negative infinity or positive infinity? Well, both. It depends on where you're looking. So here we'd say my f of x's are approaching negative infinity. As x gets bigger this way, my outputs are getting smaller this way. As x gets negatively larger this way, so are its outputs. So you're going to write it like this every time. As x approaches positive infinity, what is f of x doing? And as x approaches negative infinity, what is your output, your y values, or your f of x is doing? F of x is approaching negative infinity both times, so you just write it for both spots. You don't really need to think about that. However, here, as x gets bigger, your output is also getting bigger. And as x gets smaller here, your output is also getting negative. So that one's a little trickier. And it's just the opposite for the next one. But every time you're writing as x approaches positive infinity and as x approaches negative infinity, what are your outputs doing? Well, as x approaches positive infinity, your output is being negative, and as x is getting negatively larger here, your output is getting positive. Okay, so we're going to stop here. That's part 1. That's chapter 5.3, and then we'll come back with 5-4.